gave us the first session on mathematics for machine learning. And then Nsubuga Hassan came in and he took us through deployments of deep learning models. Mid-morning hour, we had deep feed-forward networks, courtesy of Dr. Amal Ranen Tricky. And in the afternoon, we had Mr. Benjamin Akara taking us through CNN's convolutions, convolutional neural networks. Today is our last day of tutorials. And in this last day of tutorials, we're going to have very interesting sessions, courtesy of Dr. Ulrich Paquet, Wairagala Eric Peter, Professor Benjamin Rosman, and lastly, Lisa Wang. So without further ado, I would like to introduce our first speaker this morning. That is Dr. Ulrich Paquet. And he is the co-founder of Deep Learning Indaba, and is currently working also as a research scientist with DeepMind London. He's a professor of applied mathematics in the University of Stellenbosch, and he's going to be taking us through a session with reference to from linear to nonlinear models in AI. So without further ado, I'd like to welcome you, Dr. Ulrich Paquet. Please, the floor is yours.
Bruno, hello, good morning, everyone. Bruno, maybe you could enable me to start my video. Then you could all see me as well.
You should be able to do so right now.
Fantastic. Thank you very much, everyone, and good morning. It's wonderful to see you all virtually on this wonderful Wednesday morning. My name is Ulrich, and I've got an hour to talk to you about the journey from linear models to nonlinear models. And I'm going to screen share and select Windows. Just bear with me for a second. Okay. Can you let's just see. Can you see a presentation appear?
That is correct. Can see.
Oh, fantastic. Okay. Let me also get the timer so that I don't keep you busy the whole day. So I'm going to talk to you about the how one can mathematically go from linear to nonlinear models. And I'm going to first ask you a big favor. And the first step of this morning session is to be really old-fashioned and find a piece of paper and a pen, because in the next hour, you're going to do quite a few exercises. And it's easy for me to explain things if you have time to write things down, and it'll also make it easier for you to follow. Now, admittedly, I only see one screen, and these are the slides. So if you want to ask any questions, maybe you could just raise your hand, and you could just interrupt me at any time, and maybe Bruno could moderate. So this is the first example that I would like you to draw on your paper, if you found a pen and a piece of paper. So our first example is to do basic regression with inputs X, and then what I call T for targets on the Y-axis.
Ulrich,
yes.
We only see a black screen. I think I don't know if that is the intention. With light.
That is certainly not the intention.
Yes.
That is certainly not the intention. You should see very, very colorful screens and slides. Let me try again. So let's go for a share screen, Windows screen. Let's try this one and say allow. How does this
Okay.
look?
Yeah. This
Okay.
one is yes, yes. This is it. Correct.
This
Oops.
looks better.
It's gone back. It's gone back to the same black screen with the light hands or something.
Okay, so let me stop sharing. Sorry for the technical glitches. So it seems as if the only way I could share the entire screen.
Yeah, that
There
would
we
be
go.
actually adequate. Yes, yes. Yeah, sure.
Okay, this works now.
Perfect.
Great. So I mentioned step one for all of you is just to get a pen and paper and be ready to write down a few things. And the first thing I'd like you to write down is to just copy this picture, because we're going to reuse it a number of times. And it's a simple regression task where we have 4 data points, X, and then on the Y-axis, we have targets, or what I call T. So I'll give you just a few seconds to copy this down. This is really easy. And what we would like to do is find a function that fits the data, fits the targets given inputs X. And we use this to slowly move from linear models to nonlinear models. And so once you've copied that, we'll use the following notation. So just so that everyone's clear, because sometimes if you just show people mathematics on a screen, everyone goes, wow, what's going on? So our input variables are X, they're d-dimensional. We'll make them like a fat letter if it's a vector. And an example is this X, which is a sequence of numbers, is a vector below. So X is our input variables in the picture that you just drew. And what we'll do in the next hour is I'll explain the transition from linear to nonlinear models in 3 parts. The first one would be models that are linear in their parameters and linear in their input variables. The second part would be models that are linear in their parameters, but nonlinear in their input variables. And then the last part will be models that are nonlinear in their parameters, and then also nonlinear in their input variables. So let's start with models that are linear in their parameters and linear in the input variables. And I'm going to take all of my examples from this excellent book. It's called Pattern Recognition and Machine Learning by Chris Bishop. So Chris is the director of Microsoft Research Cambridge and also Microsoft Research Europe. And this book was written 10 to 15 years ago, and it's available for free online, and it's absolutely fantastic. So I'm taking many of the examples out of chapter 3 of this book. So if you'd like to make a note of the title and Google it and see if you can find the PDF for free online. So let's start with linear models that are linear in their parameters and linear in the input variables. So the simplest example is linear regression. So here we have a function. The function is called y, and it's a function of 2 things. It's a function of x, the input, and it's a function of w, a weight vector of parameters. And it simply says that we've got a vector w, and it's got a w0 bias plus a weight times x1 plus all the way to a weight times xt at the end. So now I have a question for you. What kinds of functions can you create with this? So I'll give you 30 seconds to try and draw a few example functions on your piece of paper or in your book, just so that you're up to speed. What kinds of functions can you create with this? Draw me a few. Because I can't see you, so I wouldn't know when you're done. And usually I would walk around in a class and just double check that all the students are participating, but I trust you are. And the kinds of example functions that we could draw all look like this. So so they're all straight lines that try to interpolate the data. So I trust that all of you drew some function that looked a little bit like this as a linear function. But this is a very, very restricted class of functions, linear in parameters, linear in the input variables. And we'd like to do something more complex, nonlinear. And so we are going to make a little jump to functions that are linear in their parameters and now nonlinear in the input variables. So, so just to loop back a little bit, if you looked at the linear regression function, do any of the x's have powers in them or appear in strange other functions? No, you just see the x's as they are. And do any of the weights appear in powers or any other funky strange functions? No, you see the weights w appear just as they are, and you've got an inner product w times x. So it's linear in w and linear in x. So to make it nonlinear in x, we're going to do funky things with the x part, with the input variables, and that's what we'll do next. So let's move to functions that are nonlinear in the input variables. So here is an example. And I'll explain this very, very slowly over a number of slides. So here, I've done exactly the same thing as I've done with the linear function, except that I wrapped, if you can see my mouse pointer, I've wrapped a little function phi around the x. So in the previous example, we still had a sum over w's, like w times x. Now we've got a sum over w's times a little function phi of x. So this function is called a linear basis function model because it's linear in the parameters w, but it is nonlinear in the input variables. So to make sure that you understand the notation, I'm going to ask you to write down on paper what the function y of x and w looks like for these two basis functions. And the two basis functions are phi1 is equal to x1, and phi2 of x just picks out the second component of x. So I'll give you 30 seconds to try and write down the function y if these okay. If you've done writing it down, that's roughly what your answer should look like. You have a linear function again. And you have a linear function because your two basis functions were linear. Your two basis functions just said, I pick the first and the second component of x1 and x2. Okay, great. So you've all done that. Let's try another example. So now I'm going to ask you to write down the function y again. But now use this set of 5 basis functions. So your function is going to have 6 terms. It's going to have a w0 constant or bias term, and then there are going to be 5 terms in there, and then there'll be a sum of 5 things. Let me give you 30 more seconds to write this down. And I'd really like you to write it down because otherwise I find that if I listen to online talks and I just stare at mathematics notation, I get lost within 5 minutes. So this just ensures that everyone stays with me. And okay, so let me just go through the basis functions. The first one just takes the first component of x. The second basis function takes the second component of vector x. The third basis function takes the first component of x and it squares it. The fourth one takes the second component and squares it, and the fifth one takes x1 times x2. And what you should write down is something that looks like this. Oh my goodness, it's a long expression. It's got 1, 2, 3, 4, 5, 6 different terms. And if you look at this expression, you'll see squares around the x1 and the x2, and a product of x1 and x2. So now this is suddenly linear in W, but it's not linear in the input parameters anymore. So I'm going to give you another little challenge. And the challenge is to look at this function. And on the piece of paper that you have with you, try and draw what kinds of functions you can create with this setup. So on your piece of paper that has x as an input and t as a target, you draw functions y that would correspond to this this expression. You can shout out if I'm going too fast, or you can also press the fast forward button if I'm going too slow. I'm joking. There's no fast forward button. But what you should draw is a function that might look like this, or the other way around. So the functions that we've just created with this set of basis functions is all quadratic functions, or all parabolas in 2 dimensions. So now we could fit, with this set of basis functions, we can fit parabolas to the data, we can fit quadratics to the data. But it may be true that our data is more nonlinear than just a quadratic function. We may need a richer representation of a function to capture our data. So I'm going to move on to another one. So before I do that, I'm going to make our notation a tiny bit simpler. So we had our first component was a W0 like that. So I'm now going to write this as W0 times 1, or W0 times the basis function as 1, so that we could write our function y as an inner product between w and then all the basis functions. So here you can clearly see that this function is linear in the parameters, but it could be nonlinear in x, and we call this a linear model because it's linear in the parameters. So that's the function we're going to use. Okay, so given this notation, can you write down as an exercise, write down the function y for these 3 basis functions? This begins to look very interesting. So the first basis function is just 1, it's a constant. The second basis function is an exponential, e to the power of x minus some centroid squared. And the second basis function is e to the power of x minus a second mean or centroid squared. Okay, so the form of the first basis function here is like a Gaussian distribution, it's just a bump. And the form of the second basis function is a bump. And these bumps are centered on mu1 and mu2. All right, take 30 seconds and write down these two, this y as a long basis, as the long expression. Okay, so you're going to have 3 terms in your expression. So w is going to have 3 components, and if you're done writing this down, your answer might look something like this. So y has 3 terms, w0, 1, 2, and then my 2 basis functions, actually the first one is constant, and my next 2 basis functions are just bumps that I weigh up and down. So I can make them bigger or smaller if I change w1 and w2. Are you all with me? If you're all with me, then I'll ask you another challenge on paper. And the challenge for you, where you could raise your hand if you were in class, is like, what kind of functions can we create with this setup? Take 30 seconds and try and draw a few example functions that we could create with this y, with this linear basis function model. So in a class, there would have been someone in the back row saying, yes, sir, I'm done. I've got it. I've got it. I've got it. And so maybe you've got it as well. And your answer might look something like this. So here, you would create any function that's a weighted sum of these two bumps. So it could go up really high, and there could be a tiny bump over here, or if you make this blue bump small, there could be a tiny bump there and a big bump at the end. And these two are centered at 2 points, where the first one is where my mouse pointer is, and the second point is where the centroid where my mouse pointer is. And those 2 points are the mu1 and mu2 centroids of these two bumps.
Just a moment, Doctor.
Yes, sir.
Mr. Emmanuel is asking, why do we transpose the parameter W?
Oh, okay. I wish I had a pen and paper here. So here is a transpose up there, because usually we write vectors as column vectors. So in this case, if I take this phi of x and I would just stack them up 1, 2, 3 in a column, that column where my is stacked with 3 rows and 1 column, that would be phi of x. Now W would also have 3 components. And the rules of matrix multiplication says that this W on its own would also have 3, W1, W2, or W0, W1, and W2 in a column. But the rules of matrix multiplication says that if the output should be a scalar, this W should lie on its side. It should basically be like a stickman that lies flat on the ground. And this phi vector should be like a stickman that stands upside down. And that says that you multiply the first element of W with the first of phi, and you multiply the second one of W with the second one of phi, and third, and you add them together, and that gives you a scalar or a number as an output. If, for instance, there was no transpose there, but I put the transpose at the end of the phi, the answer would have been a 3 by 3 matrix in this case, and not a scalar. I hope that makes sense. So if this W is a 3 by 1 vector, or a 3 by 1 matrix, this W transpose, and this phi is a this W transpose is a 1 by 3 matrix, and this is a 3 by 1 matrix, and then it becomes a 1 by 1 matrix or a scalar in the end. So this is another way to write an inner product. I wish I had a nice blackboard to draw you the picture, but this W transpose is like a stickman that lies on its side.
Doctor,
yes,
maybe you can use the annotation tool on the screen share. The annotation tool. Just down, you should be able to see it under the list of menus. There is annotation.
Let's try.
Annotation. Yeah. Yes.
And under more.
Yes.
You know what? I am presenting this from a browser, so I don't have the annotation tools with me. I'm so sorry. I wish I had the annotation tools. But is this roughly clear?
So maybe Emmanuel will indicate to us. Emmanuel, you can chat. You can send us a message to confirm that you have understood what doctors explained.
Otherwise, I can draw it in real time. So W transpose will look like this, and then phi of x will look like this. Whoops. So I know this is like real-time drawing. So this is this thing that I've drawn here and let's make it red. That is W transpose, and this oopsie daisy, and this over here in blue, that is phi, and the product of them with the rules of matrix multiplication just says that 1 by 3 by 3 by 1 vector, if I were to multiply them together, that's going to just give me, let's make this green, the scalar in green. Okay, so so this y over here, if I just continue presenting, this y over here is a scalar, it's a number, it's a function. So that's equal to this, it's a 1 by 1 matrix, it's a scalar. And this W transpose is this 1 by 3 vector. And this phi is a 3 by 1 vector. And if I multiply them, I do first times the first, plus the second entry times the second entry, plus the third entry times the third entry, and bingo, I get my scalar out. I hope this makes sense.
Yeah, he's got it. He's got it.
Okay, got it. Okay. I've actually seen many people assume that t is like raised w to the power of t. That's not what's happening. That t is just a sign that takes like a stickman that stands upright and it puts it flat on its stomach to lie on the ground. It rotates it by 90 degrees. Okay. So did you all draw functions that are weighted sums of these bumps? And going back to the example here, our 3 basis functions are bump 1, and bump 2. And so in this phi vector, this blue one, at the top of my mouse pointer, that's where the 1 will appear. In the middle, that's where bump 1 will appear. And at the bottom, that's where the value of bump 2 will appear. And then, of course, this is W1, W2, and W3. So the middle W gets multiplied with bump 1, and the last W gets multiplied with bump 2. So if I make the middle W negative, I actually make bump 1 go down. So I can make bump 1 go up and down, and I add them together. Okay. So these models are called radial basis function networks, and they were often used in the 90s in the deep learning, well, what is there in the deep learning community. They have a big disadvantage, and they're not great for modeling data that is out here. So for instance, I can make this pink bump as big as I want. In this tail over here, my function will always be approximately close to 0. So what people often do is add a bump on every data point in their data set. So here are more examples of basis functions. So we've written down polynomials. You drew a quadratic function. You drew lots of bumps. And here in the middle is a whole collection of bumps. So in this case, I said, let's use 2 bumps. This person said, well, there's going to be a problem because I can't fit data out there at x equal to 7. So this person just used a whole sequence of bumps to cover the whole range of the input space. And there we have polynomials in this example. If you go to Chris Bishop's pattern recognition book that you could download for free, I copied these examples from his chapter 3. If you'd like to take some time and slowly read through it. There are many other basis functions that we could choose. You could use sine and cosine functions, which work in their frequency. And you might have heard of Fourier analysis of Fourier basis. And there's Mr. Joseph Fourier, the Frenchman from the 1700s. That's just a particular a choice of basis functions. Another set of basis functions people use in signal processing are wavelets, but we'll just say that there are many more basis functions that you could choose in these linear models. Okay, so now we get to the mega question. So now we have a model that's linear and in the weights, but it's still nonlinear in our parameter in our inputs because we have all these basis functions. How on earth will we infer the parameters of a linear basis function model? And we're going to make some assumptions. The assumption is that our target, t, is equal to the blue line, y, plus epsilon. And epsilon is additive Gaussian noise. It could be any other noise model. So it just means that someone that assumes that the points actually start really on the blue line, and then they're fudged up and down. And to fit the parameters of such a model, we'd like to make these orange differences as small as possible. And of course, every time we change the weights, the line moves. Okay, now I'm going to take a probabilistic interpretation. If you're not familiar with probability theory, you can skip the next 3 or 4 slides and just slowly listen. The first thing I'll do is I'll put a Gaussian distribution on the function value y. And the Gaussian distribution will have a mean of y, of the function, and it's going to have some spread. So this pink distribution will be very wide or narrow with some spread. And I'll say that the probability distribution of a target, this blue dot, conditional on the input x, all the weights that I've chosen, and some width of how much error I tolerate, is one Gaussian distribution. So this may look really strange to you. So to make the picture clearer, I'm going to take this whole picture drawing and I'm going to rotate it on its side. So let's rotate it. So I'm rotating it now. That looks better. So now, this rotated picture, you can really see in this pink line that we have a Gaussian distribution. The mean of the Gaussian is exactly at y of x and w. And the thing we want to predict is how far t is from that mean. And we've got some spread or variance. That's one probabilistic interpretation of a model. Okay, so I hope you understand how I get to this Gaussian distribution. Simply from this equation, my target is my function plus a bit of noise. The target is the function plus a bit of Gaussian noise that puts the blue dot right over there. Okay. The rules of expectation just says that on average, the expected value of my target given x at the bottom is going to be the blue line. So all that says is that if I were to put a line in the middle of lots of data points, the line will be on average in the middle of them. That's all that the expectation says. For those who love mathematics, it's the integral of t times the probability of t given x and w and b integrated over t. And if you compute that integral, you put a little t in front and integrate out, you just get the mean. So on average, my function is the data fits. So to infer the parameters, I'm going to introduce a little bit more notation. And the notation is to have t1 to tn, my 4 targets, where n is 4, and then x1 to xn, my 4 inputs. And I'll put the 4 inputs as a matrix. And the parameters will be inferred by assuming that all 4 of them, 1, 2, 3, 4, are identically distributed. So I've got targets n equals 1, 2, 3, and 4. And for each of them, there's a little Gaussian distribution. So I've got a product of 1, 2, 3, 4 Gaussian distributions on the 4 data points. And that's the probability distribution of all my targets given all my data and my weights of my function and some parameter that tells me about the noise. And this function over here, this this y, that's just w times my basis functions. That's very familiar to you by now. That w transpose is the stickman w that lies on its side, and this phi is just the upright stickman. Then they're multiplied in an inner product. Okay. Now this is the last, well, second last mathematically more challenging part. Is I'm going to ask you to write down the log of the probability of t given x, w, and the noise tolerance. So take 30 seconds and try and write down the logarithm of this expression on a piece of paper. Okay, so the rules of logarithms says that if I were to put a log in front of this product, products become sums. So there's going to be a sum that says n equals 1, 2, 3, and 4. And then there's going to be the Gaussian parameters. In the interest of time, I see we've got 20 minutes left, and I want to leave time for questions. So I'll just ask you first, how are you doing? Are you keeping up? If you are, I'll write down the log over here very slowly for you to see. So the product became a sum over 1, 2, 3, 4 data points, and then I've got the log of the Gaussian. And if I were to write out this logarithm of this Gaussian with the mean at the function, I'd get an expression like this. There'd be some constants that I can ignore, and then finally there's a term that is the error that over my data. And that term is the one we'll examine. If you don't like the probabilistic interpretation, you can ignore all the rest and just write down this E as your error function. So this is the error, or my loss function. It says that I sum over all data points, and I just take the target, and I take the difference between the target and the function, and I square them. So let's see if there's a, did I put a picture down? Yes, I did. So this is the maximum likelihood solution. Let's look at a picture of what this loss function actually does. So this is the loss function. Again, I copied it over to the top. So let's go through it slowly. It sums through 4 data points, 1, 2, 3, 4, and it takes the difference between every target and every blue function, and it squares it. So if this is my blue function and these dots are my target, the first difference is exactly the length of the orange line. And the second difference in the sum is exactly the length of the second orange line. And the third difference in the sum is the length of the third orange line. And yes, you've guessed it. The fourth difference is the length of the fourth orange line, which is tiny. And so how would you fit data? Well, I would like to make these lengths of these orange lines as small as possible, because if they're tiny, 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 I've got a really nice fit to the data. If these orange lines are really long, I would know that this function is way off. So if I minimize this loss function, I essentially make all the orange lines as small as possible, and that gives me like a nice fit to the data. Okay, so we want to minimize E, the loss function. Is that clear enough? Okay, so let's minimize. So to minimize, we actually need to go downhill. Like we want to make the orange sticks shorter and shorter and shorter and shorter. So to go downhill, to make the sticks shorter and shorter and shorter, we need a gradient. We need to know in which direction or how to change my weights to make those orange sticks shorter. So you can try and write down the gradient of your loss function with respect to a whole vector. If you've never done that before, I'll explain this to you in the next few slides. I'll give you 30 seconds to just try for yourself. That'll also keep you fresh on the notation. Okay, so my loss function is the sum of squared errors. It's linear in W, which is great. We can take gradients of things that are linear quite easily, and we'll do it in the following way. So let's start with this sum of squared errors. So what do the rules of gradient say? I want to take the derivative with respect to a whole vector W. And the rules of derivatives say that, well, this W sits inside a square. 2 over there. So the first rule says, I take this 2 and I put it in the front. And then that power becomes 1 less. And then the inner derivative says, well, now I should take the derivative of the expression with respect to W. And it means that W disappears and this vector remains. So going to take this 2, it jumps to the front, it multiplies out of the half, and it's gone. And the second phi jumps to the front or to the back. And this is just following the rules of differentiation. So if I were to do this 2 jumped to the front, and the half got multiplied away. So there's no more half in there. And the term that's linear in W, this extra vector just popped to the back. Like that, and there's a transpose because W had a transpose. And you could look up these rules for differentiation for vectors in the matrix cookbook. There's a book called the Matrix Cookbook online for free as well. So that's the gradient. So if you compute that, you know exactly how the W should change to minimize it. Okay, and so now the challenge is to multiply out the gradient and set it to 0. So how do we multiply the gradient out? Well, I'm going to take this vector. So remember, it's at the back of the brackets. So I'll take this vector and I multiply it into the t's, and I multiply it into that expression over there. And that's how I'll get to the next slide. So I'll multiply this into the targets, and I'll multiply this into the basis function vector. And to multiply it in, I've just multiplied that in, wham, bam, over there with the t's. So that gives me the first term. And then I've multiplied it in to the back, and that gives me the second term. So if I want to set the gradients to 0, actually like find the best possible fit and find out what the values of my weights are, I need to set the gradient to 0, and that's then what the expression looks like. So it's quite easy. We just set this to 0, we multiplied it in, and then we get this expression at the top. Okay, now we need to set this to 0 to find the weights. And I'll show you how the algebra works to do this. So to set this to 0, so I've just showed you where the 2 terms come from. To set this to 0, I'll first of all get rid of the 0 on that side. And I'll take this whole part and I'll whop it on the other side. So I'll get rid of the 0, and then the first term should be equal to the second term. That'll still help solve for the weights. Okay, now we need to get these weights on their own. So bear with me for a little bit more algebra. So to get those weights on their own, well, these weights are almost on their own, except that they're post-multiplied by this matrix. So to get rid of the matrix, we multiply both sides with the matrix inverse. So we multiply with the matrix, this thing's inverse on that side, and what we do on the right-hand side, we should also do on the left-hand side. And once we've done that, this last term will disappear, and we've got W on its own, and the weights would be equal to whatever thing we've calculated on the left-hand side. And we're done. We've actually analytically minimized and fit the parameters of a linear basis function model. It's fairly easy to do in a few lines of code, but the derivation takes a bit of time. So I encourage you to take Chris Bishop's book and just go through it at your own pace. So this is our ta-da moment. We've got an expression for the weights. So let's do it in a little bit more detail. And to do it in a bit more detail, and we've got 10 minutes left, so I'll just briefly show you how it's done, is to get, first of all, to get rid of all these sums. And I'll get rid of the sums by writing this as a product between two matrices. If you don't understand exactly how it works in 5 minutes, because I know it's quite a lot, then don't worry at all. But to get rid of these sums, I'll construct something that people in machine learning or AI call a design matrix. So I'll construct a design matrix, fat phi at the bottom, and the very first row of phi will contain, well, okay, so phi will contain all the data points along its rows. So I'll go data point 1, 2, up to 4, or up to n. So in the very first row, I'll put the basis functions for data point 1. It's just a vector that I slap in there. And you've guessed it, in the next row, I copy the basis functions for data point 2. And so I continue and continue and continue until in the very last row, I put the basis functions for my final data point. And that gives me the design matrix. So this expression in this green square is the design matrix times itself transposed. I'll also do something with the left-hand side, and I'll get rid of that sum over t. So I'll just take all the targets t, and I'll put them in one long column vector. So this is like a stickman that stands upright. So this first expression is the targets times the design matrix, that one over there, and this green one over there is the design matrix times itself. And because we had to get rid of it with the inverse, to slap it on that side, there's a little inverse there. Now, it's a lot of matrix multiplication to digest in 2 minutes. So all we declare here is victory, ta-da-da, we've got it, we did it. And then I'll leave you to read Chris Bishop's book to find out the details. But this gives me an expression for the weights analytically. And there's the inverse. So now I can analytically fit any radial basis function network or any polynomial. So here I show the best fits for polynomials degree 0, so it's just a constant, degree 1, degree 3, and degree 9. So degree 9 is like x1 or x squared, x3 up to x to the power of 9. And what you clearly see over here is that there's a phenomenon that happens where your model is not rich enough, and this is called underfitting. Like you don't even get close to your data. On the other hand, you're completely over-optimistic and you fit all your data perfectly, but you don't actually interpolate the true function at all. You just bob up and down and you're all over the place. But look, your error is 0 because you actually fit the blue data points exactly. So it looks amazing, but actually it's not that amazing. You're after something that looks a bit more like this picture. If I were to plot the weights for each of these functions, the weights, remember in this one there are 9 weights, the weights look like this, the best possible weights. So there's sort of 0.1, then 0.8 for this function, then sort of up to -25 for this function. And then to get this perfectly into interpolating fit for a 9th degree polynomial, my weights take on crazily big and small values, like the best weights. So the weights that find these, interpolate these data points are big in magnitude. So to prevent overfitting, like we see in this example, people often penalize the weights from getting too big. So you don't want super big weights because that tends to overfit. So you'll add another term to your loss function, and that is called a regularizer. So it's just a lambda, it's a scalar, times another error or loss function. That's a function of the weights, and it should just ensure the weights aren't that big. So how will you ensure that your weights don't get mega big and overfit the data? So there's my loss function, and then I add something to it, a scalar times an error term. Just take 30 seconds, and with a few minutes left, this is an example of an error term. For the question of what does the transpose do, so this error term here, the regularizer term that makes the weight stay small, this just says that it's the sum of all your w's, sum of all your w squareds. So it's w1 squared plus w2 squared plus w3 squared. And of course, to make that small, all the w's should be small. So you'd add that to your loss function, and you'd regularize your solution. So regularized just means that you make things more regular and smooth than the crazy answers we saw earlier. So if we do that very, very, very carefully, we could actually take our 9th degree polynomial, this one that in a few slides ago was crazy, crazy, crazy in the way it bobbed up and down, and we force the weights to be smaller by adding this term, and we could actually get a function that interpolates the data fairly nicely. And this is for a tiny lambda value, a tiny contribution to the regularizer. If we make this lambda too big, then of course the weights can't be anywhere but 0. And so if the weights are too big, then even with a 9th degree polynomial, you're going to underfit because your weights just can't go anywhere. So there are many techniques to actually find the best value for this regularizer, this constant. Okay, there are many other options for what that loss function could have been. So it could be the sum of absolute values, for instance, and they all have different properties. So this is with a 15th degree polynomial. Sorry, with a 9th degree polynomial. So if I add more data, and I don't regularize, things of course get better as well. So here I have more data points, 15, than I have degrees in my polynomial, which is 9. So of course now it doesn't crazily fluctuate up and down anymore. If I take 100 data points and I don't regularize, my fit gets smoother. So you can always make your fit smoother and better by just increasing the number of data points as well, without penalizing your model, at least with an extra loss term. Okay, so at the very end, let's try and see the wood from the trees. So I've shown you linear models in parameters and inputs, linear in parameters and non-linear in inputs. They were actually really nice because we could analytically minimize them and find a solution. And now finally, let's do non-linear parameters, non-linear in input variables. So far we've looked at functions that look like this. They were linear in W, and then it was multiplied with some phi, some function of the inputs. But here's an idea for you. What if this was another function of x with weights? So this phi was just like x and x squared, or a Gaussian bump around x. But you could also make it a function of other weights. What would happen then? Oh my goodness, then it's not linear in the weights anymore. So here I've taken this exact function, this one over here, and instead of writing phi of x, I've just slapped in another function of w's and x's. And now you're probably looking at this formula saying, what on earth is going on here? So I'm going to skip this and just briefly mention that to make this work, you have to add some extra non-linearities and explain it through a picture. So you've all probably seen this very familiar picture of neural networks, where you have inputs, x1 to xd, plus a bias equal to 1. And then you've got hidden units and maybe outputs. And what I want to show you is I'm going to take this function and I'm only going to zoom in on one part of this function. And that's what the part looks like. So now we've got, just looking at one output, we've got a sum of w's times basis function, basis function, basis function. And these basis functions are product or functions of like earlier x's and weights. So this expression over here is just w times my basis functions again, and these basis functions are functions of other earlier w's. And that is our segue into deep learning. Deep learning is just a composition of all these linear functions that are nonlinear in the input variables. But because it's this composition, we can't actually turn the crank and get an analytic solution anymore. I can't just write down an expression of the weights. At that point, we enter the whole deep learning land, and it's like deep learning to the rescue, but it brings a whole different set of complexities. Minimizing it, stochastic gradient descent, not analytic solutions anymore, etc., etc. Design of these functions, and I'm going to stop at this point because I think it's a nice point where I could hand over to anyone who teaches the deep learning course. And so I've taken you on a little journey from linear functions in parameters and inputs to linear functions in parameters, but non-linear in inputs. And then finally saying that when we do deep learning, we just stack them together. So it becomes non-linear in the weights as well. At very lastly, do try and find this book online for free. I've discussed most of chapter 1 and chapter 3 of this book, and a bit of chapter 5 with you in this hour. And I hope it was a nice introduction for you, and the rest you could find in the book at your own pace. I'll going to stop sharing here, and then we've got maybe a few questions and time for a chat.
Thank you very much.
Again.
Thank you very much, Dr. Ulrich, for that beautiful presentation you made. And apart from the earlier question from Emmanuel, we've not got any other question really. But
there was a question about the name of the differential calculus book. There's a book that's called the Matrix Cookbook. So cookbook as in cooking, making cookies and cakes and food. It's called the Matrix Cookbook. That's also available online for free.
Okay.
I can share the slides, but I think it's even easier. I've just copied equations and pictures from Chris Bishop's book. So if you find the pattern recognition and machine learning book online, I can maybe even try and type the URL for you. Where do I?
Yeah, that will be really helpful.
I've just typed the URL for everyone. If you go to chapter 3 in that book that I've just sent to everyone in the chat window, chapter 3 and chapter 1, you'll find everything that I've explained to you here.
Okay, we have someone who is raising up a hand. Just a sec.
Yes.
The hand is back down, so I couldn't tell who. Yeah, so I can't see the hand. It was up, then it went back down. Shall we get all the slides? So that was a question from somebody else. That is Isofel.
Yeah, you can get the slides, but the slides are copies from the chapter 3 in the book. So I'd actually just recommend reading chapter 3 in the book, and that's got all the details for you with all the beautiful text that comes with it.
Yeah, I think it's been adequate and prudent enough. We have also kept our time. I think I would like to thank you so much, Dr. Ulrich, for the time that you've taken to prepare for this material that you've shared today. Really appreciate your time. Thank you so much.
Yes, everyone, thank you. Thank you so much, Bruno, for organizing IndabaX Uganda. It's really fantastic to see it happen. Good luck, everyone, for your journeys as scientists and explorers in this AI machine learning space. It's really exciting. And I wish you all the best. And I hope that in this hour you got some of the basic tools to keep you running, and the basic tools help you understand deep models better, because they're all the basic building blocks that together make up a deep learning pipeline.
Okay, thank you very much.
I'm still a fan of learning models. Okay.
Yeah, sure. So Bruno is actually online, but I'm the one moderating. Eugene is my name.
Hi, Eugene. Hi, Eugene.
Hey, hi. Yeah, I took note that you referred to Bruno. I know you've been in touch with him. We've been part of the team. I also see my co-team players here. Claire is here, and Gloria is also around. Samia is around. So that was part of the committee led by Mr. Bruno. So we are grateful for everything that you've done to ensure that also this comes to light. Thank you so much.
Yeah, everyone, and for your team, fantastic job. This is really wonderful to see. So I should probably just let you move on to the next session, or go and have a coffee